Thank you for joining us. We'll get started in just a moment. Just a real quick logistical update while people are coming into from the waiting room. The write-ups, the initial write-ups, the very beginning, first draft write-ups for, I believe, atmospheric modeling, we're expecting Thursday, and data acquisition, we're expecting Monday, I believe. And I apologize that I didn't get a chance to ask Beth about the land modeling. So those of you who are looking to kind of see the first write-ups, just hang tight with us. They're coming in and we'll get started with that soon. So I think everybody, the recording has started, and Haruko, I'm going to turn it over to you.
Okay, so good morning, everyone. This is the day 6 of the AI4ESP workshop. It's been incredible experience for me to see all the AI machine learning application in earth science and to see a lot of excitement and great ideas from everyone. I'm looking forward to today's and future sessions as well. Today we have 2 plenary talks in this session. Before we start, I'd like to note that unfortunately we might not have enough time for questions, but you can leave the questions in our Slack channel. I shared the Slack channel in the chat, or you can use the QA in the Zoom, and we will make sure to contact the speakers later and to get answers as well. So the first presentation is by Professor Tapio Schneider. Professor Schneider is the Theodore Y. Wu Professor of the Environmental Science and Engineering at Caltech, and a senior research scientist at NASA's Jet Propulsion Laboratory. His work has elucidated how rainfall extremes change with climate, how changes in cloud cover can destabilize the climate system, and how wind and weather on planetary bodies such as Jupiter and Titan come about. He's currently leading the Climate Modeling Alliance, whose mission is to build the first Earth system model that automatically learns from diverse data sources to produce accurate climate prediction. He was named one of the 20 best brains under 40 by Discover magazine, was a David and Lucy Packard Fellow and Alfred Sohn Research Fellow, and he is the recipient of the James Holton Award of the American Geophysical Union and of the Rosenstiel Award from University of Miami. With that, I will pass the stage to Tapio.
Yeah, thank you for having me. It's a pleasure to be contributing to this workshop. So I want to talk about how to use tools from AI broadly understood to accelerate Earth system science and prediction. The fundamental problem in predicting the Earth system is bridging scales from small to large. Here's one example from clouds. It's paradigmatic and the largest uncertainty in climate predictions. What you have in a climate model are large-scale variables like humidity, temperature, and the like. What is going on in a cloud is a myriad of complex processes, for example, involving the microphysics, involving turbulent dynamics, and so forth, leading to droplet growth, growth of ice crystals, and the like. And what you really want in a climate model are large-scale effects of all these small-scale processes that ultimately determine things like the cloud albedo, cloud cover, precipitation, and the like. You might hope that brute force computing will solve this problem, and it might, but it will take much, much too long. The scales here cannot be bridged by brute force computing. They range from micrometers to planetary scales. Even just from the turbulent dynamics on meter scales to the global scale, you would need computers something like a factor 10 to 11 times faster than the fastest we have. It's just not possible in the foreseeable future. The same is true for many other components of the climate system, ocean turbulence, similar things could be said. Even the biosphere, what a climate model has that's relevant for the biosphere are variables like sunlight, CO2 concentration, temperature, humidity, precipitation, soil moisture, and the like. And then there's a myriad of small-scale processes going on in leaves, in canopies, in roots, and the like, that ultimately give rise to the emergent behavior we are interested in, ecosystem level physics that allow us to get the quantities out that we want to get for climate purposes. Again, albedo, CO2 fluxes, the surface roughness we want to know, evapotranspiration. There's something I highlighted here, solar-induced fluorescence. It's a proxy for primary productivity, which now we can measure from space. There's also something you would like a climate model to predict, so you can compare it against what you can directly measure. Computing, again, is not going to get us from the left to the right alone. We need methods for bridging the scales. We live in the golden age of data. We can even see Earth breathe from space. So here is an animation of solar-induced fluorescence. Again, the proxy of primary production of photosynthesis. This is from my colleague Christian Frankenberg in this group here, based on Tripomi data. It is quite amazing. For the first time, we have global measurements of how the plant biosphere breathes seasonally. We have global measurements of cloud cover and many cloud statistics from platforms such as CloudSat, Calypso, LiDAR, Radar, and MODIS. And we have ground-based data, data from floats in the ocean, and the like. In addition, what we have are data generated computationally. So while a climate model cannot simulate clouds well at all, it cannot resolve clouds, the dynamics alone are in scales of meters, we can resolve the meter scale dynamics of clouds computationally. So here's a large eddy simulation of a tropical cumulus field. Blue is a precipitation. The simulation has resolution on the order of 10 meters. So you can run this in boxes about the size of a climate model grid column, so tens of kilometers on the side, but you can't run this on the globe. That's impossible. Yet, in limited areas, you can do these simulations, and they provide additional data where observations alone are not sufficient. For example, for turbulent statistics within the cloud, we cannot observe them directly. We can simulate them and infer them from high-resolution simulation like these here. So what you can do to make Earth system prediction more successful is use all of these data sources conjointly. I'm leading a group called CliMA, the Climate Modeling Alliance. These are about 70 scientists at MIT, at the Jet Propulsion Laboratory, at Caltech, where we're pursuing this approach. And I outlined what the approach is. We're building an Earth system model that learns from diverse data sources, be those observations or high-resolution simulations for processes that you can simulate, uses them jointly to get the model that is more data informed on a firmer data footing than the existing models are, and we hope will lead to better predictions and better simulations. Three things are crucial if you want to use data in Earth system modeling. And I think any approach that wants to exploit AI methods broadly understood, including data assimilation methods, needs to meet these three requirements. We want to predict climate, and we want to predict something for which we do not have data. We want to predict something that does not have an observed analog. So it's absolutely crucial that whatever methods we use, that they generalize out of sample. We want people to use climate predictions for planning, for example, for planning climate change adaptation, which means models need to be trusted. This has come up before, for example, in the AV Governance talk. One ingredient for trust is that models are interpretable. It's hard to trust a black box if you do not understand what it's doing. So interpretability, I think, is essential for climate models or system models, more so than for many other use cases where deep learning methods are being used. And thirdly, you want to have quantified uncertainties, because as we have learned from weather forecasting, you don't only want to have a point forecast, an expected value for something, but you also want to attach probabilities to it so you can plan proactively and cost effectively. For climate change adaptation, again, as one example, risk estimates are essential. That means you need to have quantified uncertainties. So these are three critical requirements. And now you can ask, how do we meet them? Our view is that combining the best of reductionist science with the best of what has come around in the data sciences in the past few decades leads to success here. Using any one tool in isolation probably will not lead to success. Take deep learning. Its success rests fundamentally on over-parameterization. This leads to very expressive models. That is good. They are very data hungry, which is fine in many areas. In the climate field, we have a lot of data, but the degrees of freedom we have in data is still relatively small to the degrees of freedom in the climate systems. In that sense, we do not have very much data. And the over-parameterization makes generalizability, interpretability, and uncertainty quantification very challenging. Reductionist science, as we have practiced it since at least Bacon for 400 years, its success rests on what you may call parametric sparsity. We have extremely sparsely parameterized models. Take Newton's law of universal gravitation, one parameter that leads to a law that fits apples falling from trees just as much as planets orbiting stars. It is extremely generalizable and interpretable as a result. Uncertainty quantification within it is very straightforward, but this reductionist approach clearly reaches its limits in complex systems such as the Earth system. We would like to have a reductionist description, say, of clouds or of plant biophysics, and we have tried, but we haven't succeeded in coming up with the first principle, coarse-grained description of these systems. So our approach is to combine both traditional reductionist science with AI tools broadly understood where reductionism reaches its limits. The key, I think, insight here to use data well and be able to use diverse data sources simultaneously is to focus the learning on what matters in Earth system prediction, which are statistics of the climate system averaged in time, accumulated in time. So unlike the weather forecasting situation where you learn from trajectories, instants in time, in the climate problem, the goals are different. You want to predict statistics, and I think the objective functions should be different in the same way. If you learn from statistics accumulated in time, you immediately overcome the often stated mismatch problem between the resolution of observations and simulations. Statistics vary smoothly in time. There is no mismatch issue anymore that the model resolution does not match the data resolution. You can directly focus on statistics that matter, for example, emergent constraints, things like covariation between cloud cover and surface temperature, include them in your loss function, include precipitation extremes in the loss function, if that is what you want to predict well in the end. There's a serious downside that the loss function evaluation becomes extremely expensive because now the loss function involves the accumulation of averages, seasonal averages, for example, and typically in say Bayesian learning methods, you need to evaluate the loss function perhaps 1 million times. That's simply not possible with climate models. So the current climate is extremely informative about how climate will change. Just one example, this is from a paper appeared in Physics Today, and a few other figures were as well with Nadia Ribjivanji and Rob Sokolow. This is Arctic sea ice extent. In colors, models, in black, observations. The arrows indicate how sea ice is expected to change. The models are colored from low to high climate sensitivity, from yellow to red. And you see that their biases in the present climate correlate with their climate sensitivity, which means if you use present day observations to calibrate these models better, you have a good chance of also obtaining much better predictions. Same goes for many other emergent constraints that have been much discussed in the past few years. So data are informative. Statistics are extremely informative and helpful, but learning from statistics is computationally extremely challenging. We have found a way to solve that problem, and that way is an algorithm we call calibrate, emulate, sample. What it does is it combines proven and scalable algorithms, for example, Kalman inversion and variance used in weather forecasting for decades, with machine learning tools to accelerate Bayesian learning. So what we want to do is learn parameters theta in some map G, which is your climate model that maps parameters to climate statistics Y. And the way we do it is generate pairs of training points theta and G of theta with Kalman inversion and variance. That requires a few hundred, typically, climate model evaluations. That's doable. This is a very efficient way of solving the problem of finding good design points for an emulator of the climate system. And we train an emulator on the iterations of Kalman inversion and its variance. That emulator can be Gaussian processes, can be neural networks, random feature models, you name it. And that emulation is very cheap, and the evaluation of the emulator is extremely cheap relative to running a climate model. So you can do things like MCMC sampling on the emulator in the end to get the posterior density, to get uncertainty quantification on the parameters. The parameters can and should include structural model errors. So we do this within physics-informed, process-informed models. And I do not want to dwell on equations here. I just want to say we use equations where we have them. We systematically coarse-grain them. For example, for clouds, we use a conditional averaging approach that separates isotropic turbulence from more coherent structures like updrafts, average over them separately. And we can do this exactly. You get exact conservation laws, first and second moment equations. Everything is exact, but on the right-hand side, appear unknown functions, closure functions, parameters. Those are perfect targets for machine learning tools. Those you can learn from data. If you learn within systematic closures like that from data, you're guaranteed to conserve energy, mass, and the like, which is important for generalizability and so forth. So this is where our learning is centered. These functions can be stochastic. They should include structural error models to learn about those as well. And be happy to talk with people offline how to do that. There's some important lessons we learned that I won't have time to go through now. Just let me show you one example. For the clouds, for the scheme that we developed for clouds and turbulence, it works for all types of Earth cloud regimes, from boundary layers in polar regions to deep convections over the Amazon. Here's just one example. This is liquid water in a stratocumulus top boundary layer, and in the red, observations. In black, high resolution simulation. In blue, our parentization, which captures observations and the high resolution simulations extremely well. This solves a problem that has vexed climate models for decades. But the key is the same parentization with the same parameters works for all cloud regimes. It's truly universal. So we are pursuing the same approach for all components of an all-new Earth system model. And what, in our view, is essential to make progress here, to make sustainable progress and substantial progress, is to bet on all these three areas that I'm emphasizing here. You do want to advance theory to promote parametric sparsity. This is, in some ways, the hard legwork we have been doing in the Earth system sciences for decades, and that needs to continue. And there are new approaches you can try, like what I showed for the clouds. Or my colleagues Yuji Wang, Christian Frankenberg did similar things for the biosphere very successfully. You do want to harness the diverse data that we have. This might be ground-based data, space-based data, it might be computationally generated data. You want to harness them to calibrate the model and for uncertainty quantification. And I think the key to do it well is focus on climate statistics, on time average statistics. And you do want to use computing power, leverage it as best as we can. Again, brute force computing alone won't do, but you can, for example, use computing hardware with accelerators like GPUs to enable local high resolution simulations that you can spin out potentially in thousands of locations simultaneously within the climate model for simulating clouds, sea ice, ocean turbulence. So what you're doing is building an Earth system model that has at its core process-informed components, and wrapped around them is this layer of data assimilation machine learning tools based in good part on the CES algorithm that informs these components in the end jointly with data. Right now we are doing this individually. The goal is in the end to learn jointly for the whole system model from data. That's our approach. I should mention our funders are Eric and Wendy Schmidt, are leading our funding from Schmidt Futures. Heising Simons Foundation, the National Science Foundation, Charlie Trimble, and a few others are supporting this work. We are in almost 3 years in and a few more years to go to have a complete new Earth system model. So thank you for your attention, and I'm happy to answer questions on, I guess, the Slack channel or wherever they come.
Thank you very much for the wonderful presentation. Thank you. Yes, if you have any questions, please use our Slack channel or Zoom QA function. Yes. Okay, the second presentation is by Dr. Alison Appling at USGS. She is water data scientist with the US Geological Survey. She uses a combination of statistical, theoretical, and knowledge-informed machine learning methods to predict water quality in river and lakes. Currently, she is leading a USGS effort to advance data-driven approaches for predicting water quality and quantity. With that, I will pass the stage to Alison.
Thank you, Haruko, and thank you all for allowing me to be a part of this presentation or this workshop. I've really been having a good time already. So today I'm hoping to talk about this tension that we see between our enthusiasm for the potential of data-driven approaches and also the fact of data sparsity in the Earth systems modeling situations that we want to take on. Our data is incomplete and imperfect, and we need to deal with that. I chose this analogy of a flight simulator because I think that in Earth system science, we have the same issue as training an airplane pilot. It's expensive and challenging to get a lot of real world data or experience. So it's really important to bring in some book learning and some simulation experience to facilitate our learning on the precious real world hours or data that we're able to get. So this general idea, it can be called knowledge guidance or knowledge informed or domain aware machine learning, and is something that it goes by even more names, in fact, and has really been taking off in the last 6 years or so. That's reflected in many of the talks and conversations that we've had in this workshop so far, right up to Tapio's just now. And is also reflected in the literature where by all these different names, knowledge-guided machine learning has been growing in the number of publications over time. And the same holds for the field of inland waters, which is my area of expertise. So my first exposure to knowledge-guided machine learning was in this problem of lake temperature prediction for multiple depths within a lake. And we started by looking at a deep learning model and a process-based model at a variety of different data sparsities, because lakes do vary a lot in how much data we have available. The process-based model does the best of the two when we have very few training profiles available. The deep learning model does better as we get more and more data available for training. That's great, that's expected, and that is outperformed by a knowledge-guided machine learning approach that takes a deep learning model and adds in several elements of process guidance. So this has been driving a lot of my enthusiasm for KGML as a general idea over the last few years. But this workshop has got me thinking a little bit more about what would happen if we could extend this x-axis. Would it be the case that suddenly we would see that deep learning was outperforming knowledge-guided machine learning again when we had abundant data? I don't know, because we don't have those data for my systems, but that if we do, that would be consistent with some of what others have said in this workshop, including Xiaoping Shen last week, who in his plenary suggested that deep learning models should serve as the grand master that shows us what can be possible for a prediction problem. So let's run with this idea. Let's say, okay, there are these three regimes of predictability in Earth system science. There's this regime on the left where the quality and quantity of our theory is better than the quality and quantity of our data for this prediction purpose. There's this regime in the middle where the data is better than the theory, such that deep learning outperforms process-based models, but both are still valuable. So we're still seeing the most benefit from this KGML approach. And then lastly, there could be this third regime where the data is so good that using a deep learning model is superior because adding in any amount of theory brings in simplifications and causes the model to stop learning from all of the available data. If all this is true, then I think that there's also a possibility that this dividing line between the second and third lines, as third regimes, could be kind of anywhere in a wide area. It could be that that it's way over here, and that could be because there's some forms of knowledge guidance that really don't give us a whole lot of edge over a purely data-driven approach, or it could be way over here. We have a wide variety of approaches to using knowledge-guided machine learning, and I'm trying to reflect that in this slide. But just to simplify it a bit, I think what we're talking about in figuring out where this line is, where knowledge guidance is helpful to prediction, one thing we need to consider is the domain we're working in. How challenging is the domain? How good is our theory? How good are our data? And what specific question are we answering? And are our theory and data relevant to that? In the areas I've been working, I think the answer has generally been that knowledge-guided machine learning is still favorable. And one thing is we've been working in a semi-challenging domain of water quality or temperature prediction. We don't have all the data that we might like for that prediction problem. And we're also trying to extrapolate at large scales. We're trying to predict for lakes and river reaches for which we don't have observations at all, or for which we have just a few. spatial extrapolation is generally one of those areas where we've talked a lot about the weaknesses of machine learning on its own for making good predictions and the potential for knowledge guidance to help with that. We're also trying to make extrapolations in time. We're trying to make 7-day ahead forecasts to support decisions about how much water to release from reservoirs to support cold waters downstream for fish. And we're trying to make multi-decadal predictions to look at the effects of climate change on water temperatures in future decades. And again, this is an extrapolation question. Maybe that's why KGML seems to be working for us. So then there's also this y-axis to think about and this choice of what kind of knowledge guidance we're bringing to the table for a problem. And today I want to talk about a proposal that maybe there are 3 elements to the kind of knowledge we're bringing in that might structure where we fall in this space. So there could be an element of correctness to what kinds of knowledge we're bringing in. Some knowledge is more correct, more precise than others. There's an element of novelty. So how new is this knowledge relative to what the model can learn from the data alone? And lastly, there's forcefulness. So we can sorry, I'm clicking things. We can apply our knowledge guidance with more or less aggression or assertiveness in a few different ways, and that can affect how well our KGML approach works. So here I'm just putting these 3 elements on axes together to show how they relate to one another. On the y-axis, we have correctness. So we do have some theories that are completely true and completely precise right down to the elemental physics. And we also have some ideas that are more approximate and that describe patterns a little bit more than they describe underlying fundamental processes. And this is something that's been recognized back in the DOE OSCE report in 2019 on scientific ML. We said a particular challenge is to incorporate uncertain or incomplete or multi-scale information. And just last week, we were saying in the hydrology session that one of our challenges is to figure out what to do with systems that lack reliable process representations. So the degree of correctness in what we have to offer can vary. At the same time, there's this question of novelty. So we might provide really high quality information, but it might be something that the model can already learn from the data. And so it would just be redundant. Whereas if we have really novel data, I think that means a few things. It means it's unique relative to the theory, or sorry, the theory is unique relative to the data. The theory is relevant to the question we're trying to answer. And the theory is unique and relevant everywhere in that spatial or parameter domain that we're trying to make predictions in. So given the position that we are in for correctness and novelty of a certain piece of process guidance, we might want to think about using different levels of force to bring in that guidance. And so we can adjust our forcefulness using tools like adjusting the weights on specific loss terms that reflect knowledge guidance, or adjusting the number of epochs or the learning rate in specific phases of training that are knowledge guidance focused. Or we might add in flexibility to our fudge terms or functions within models that have hard knowledge guidance constraints. And so there are lots of different tools we can bring to adjust this forcefulness. And the idea is to get the forcefulness matched to the degree of correctness and novelty. To put more of a human face on this, let's think about the expert learners that we see every day, children. If we provide guidance to them, they can learn, and they also learn from their environments. So if we're under forceful or maybe incorrect in the guidance we're providing, we might end up with a creatively painted living room, maybe not what we were aiming for. If we are under novel or over forceful in the guidance we're providing, we might bore them and we might inhibit their ability to learn from the other stimuli in their environment. And so with machine learning and with children, I think we're seeking this sweet spot of productive guidance where we're allowing them to learn from both the theory and the data. So for the rest of this talk, I'll be going through some examples of how my team is applying various forms of knowledge guidance and how it fits into this conceptual framework. And I want to start with something that is pretty fundamental, which is that there are these machine learning native forms of knowledge guidance, like recurrence, like convolution, that get us space and time awareness and are so important in so many different domains that they have become out-of-the-box options in just about every neural network implementation software. It's easy to do an LSTM, but that doesn't mean it's unimportant. Getting the space-time awareness really helps. And so Xiaowei Jia just published this paper this summer showing that he could combine LSTMs for time awareness with graph convolution for space awareness, specifically in this river network, where we were using graph convolution to allow something like routing of water along the river network. And the model could learn some of that, and we provided some of it. So when Zhao applied these three techniques of a plane neural network and then time and space-time awareness, he found improvements in RMSE as we moved up to that most complicated model. And especially in this situation, we were training on a relatively data-sparse situation, in this case, 0.1% of the observations in the very well-observed Delaware River Basin. Whereas he also looked at training on all of the abundant observations in this particular basin and found much more subtle differences among these three different approaches. So I think the difference here is not in the correctness. Both of these, these sets of architectures have similar correctness, but in the novelty. So when we have a lot of data, the model is able to learn, maybe memorize a little bit more about how it should respond rather than learning about these spatial and temporal relationships. Simon Topp, who's a postdoc at USGS and also a collaborator on this Exosheds DOE funded project, has been exploring an alternative to the LSTM graph convolution approach to space-time awareness, and that's the graph wavenet approach. It just does things a little bit differently, but it matters. And so Simon is finding that for a baseline test where we're training and testing on pretty similar data sets, the graph wavenet in purple is outperforming the RGCN that I showed on the previous slide. And that's also holding for these out-of-bounds prediction tests where we're trying to extrapolate to new climates. So I think the lesson here is that different architectures can lead to different levels of correctness by guiding the model, offering the model ways to learn about space and time relationships differently. And so these choices of machine learning native guidance will continue to be something that we want to think about as we're designing KGML approaches. So also Janet Barclay, also on the USGS and DOE Exosheds project, has been thinking about a different approach to KGML that starts with this observation that stream reaches that are heavily groundwater influenced, either deep groundwater or shallow groundwater, tend to have worse RMSEs, worse accuracy than those reaches that are atmospherically influenced. And so Janet's been leveraging this physically motivated understanding that groundwater influence can be reflected in the relationship between air temperature curves over the course of the year, shown here in black in all these panels, and then water temperature curves, which for deep water deep groundwater tend to be dampened relative to the air temperature, and for shallow groundwater are also lagged. So Janet's taking these lags and dampenings and quantifying them and asking the model and the loss function to be consistent over time. Given a reach, the lag and the dampening ought to be the same every year, and they ought to be consistent with the observations we have available. This approach is really new. She's just been on this project for a couple months. And is finding already that the deep learning and the deep groundwater and shallow groundwater sites are responding positively. We're able to make better predictions there than we were before with these new loss terms. On the other hand, we're getting worse performance for the atmospherically influenced models. So there's this difference between reaches, and I'd like to suggest that maybe that's, we know that the correctness is kind of approximate, but maybe there's this further issue of novelty. Where this information is really novel for those groundwater influenced sites, and it's important to provide it there, but it may be a little bit less novel and a little bit more approximate than we need for these atmospherically influenced sites. So next steps for us are to explore this balance of forcefulness and information to see if we can get the performance to be better across the board for these different types of sites. So the last general approach I want to talk about is data augmentation using the technique of pre-training. So we're training our machine learning models in two phases. First, we're using a process-based model to generate predictions everywhere and for all time in the domain of interest. We're training a machine learning model to emulate those predictions here in green, and then we're fine-tuning on whatever observations are available, whether they're sparse or abundant, so that the model is learning from a larger data set and potentially from more different scenarios. So going back to Zhao's work, predicting with a graph convolution neural network in the Delaware River Basin, we're finding that the influences of pre-training are positive for both the time-aware and the space-time aware scenarios. Again, when we have this data sparsity condition, when we have abundant data, again, we're seeing more of a subtle effect, still an improvement, but much less, suggesting that here, as with the architecture choices, there's this issue of novelty that affects how useful our KGML approach is. And very lastly, we've got this pre-training project, or sorry, forecasting project, where we are using pre-training and data assimilation and some other approaches to forecast 1 to 7 days ahead. We're getting good performance that's supporting decision-making about reservoir releases, but we're unable to do one thing we like, which is to predict the effects of a hypothetical water release. We can get the model to say, yeah, the water downstream is going to cool, as we would expect, but it cools at about 1/4 of the rate that our expert knowledge would suggest. So we need to get the model to be more responsive here. And one we're going to try to do this is with more pre-training scenarios using the process-based model to simulate releases. So pre-training is really cool because it's giving us this opportunity to think about situations that we have never seen in our data, that may be challenging for us to operate under, and that could be important for future projections, and while at the same time benefiting from the observations we do have. So I just want to sum up with a list of the challenges that I think I'm talking about in this presentation. One is that we need to, as we're moving into increasingly challenging domains, we need to continue to strive for correct and novel forms of knowledge guidance. But also let's continue to think about this idea of usefully forceful and tools for deciding what the right amount of force is, so that we can take advantage of the not quite correct and the not quite novel knowledge that we also have at our disposal. So thanks so much. Looking forward to the rest of this workshop.
Thank you, Alison. That was a great talk. And I would say there is one question, Alison, in the chat, and it's thanks for a great presentation. What is the data sources of the water temperature? Is it point data or picture data? And it was in earlier in your talk.
Yeah, so we've talked a little bit about using remote sensing data, and in fact, Jared Willard is leading a project now that's getting at that, but it's not out yet. For the most part, we've been using point data, but sometimes continuous point data.
Great, thank you. And Tapio, thank you so much for answering the questions. We'll grab these questions and answers and put them in the WS questions part of Slack, just to make sure that anybody who wasn't multitasking and seeing those gets a chance to see them. I really appreciate our speakers. And if everybody was not motivated after those 2 talks for today, you weren't listening. So that was wonderful. We have aerosols and clouds coming up, and then knowledge-informed machine learning after that. We'll take a quick break here. Just remember, everybody, when you jump into the sessions, please treat everybody with respect. Remember what a broad group we have, and everybody's coming from different perspectives and may not even have been exposed to the science that you're doing, the techniques you're using. So just be a little extra careful. And we appreciate everyone's constructive and challenging criticisms. And we look forward to what's coming out of this. So we'll break and see you at 1:45, if at all possible. I realize it's late and we might have a couple of lingers. So just switch over as quick as you can. Thanks, everyone.